Good morning, everyone. Today will be even worse than yesterday. I'm going to start off by giving a very talky overview of the model. I'm just going to go over some of the components that seem to come up a lot when we talk about it with others. So this will be kind of a sweep of the components of the model, not in terms of what it's capable of, like what Alistair did yesterday and what Bob will do next. This is really about the code, the files, the way we code, etc. So this is going to be very much a Fortran style presentation. As before, these slides are online. I am not good with the chat. Could somebody post that in the Zoom chat for me? I'll keep that up for a second if people want to pull it up. No, you click on it, copy link, and then go and. Oh, really? Oh, that's ridiculous. Oh, then I'll do it. I'm sorry. I really can't go to the chat. Oh, okay. You can skip the last one because there's a link. Okay, great. All right. So let's just go over what's contained in the repository when you grab it. So first of all, I have people moving around. Okay. So the directory where most of the magic happens is the source directory, src. On top of that, we have the config source, which we are already familiar with when we were playing with the list pads and MKMF tools yesterday. So config source is kind of a bit like the optional directories, although optional is a bit strong because some of them are needed. But that's the place where we sort of pop in and out the code that we may not use at compile time. The third directory that you'll see if you look through that directory is PKG. This is also code, but this is a special kind of code. This is code that we pull from other repositories and just cram right into the ARG repository and pretend it's ours. So what happens is that these come in through the submodules that you have to deal with the recursive flag. And we have symbolic links that go into the source directory. So that's why when we built this, you needed that -L flag with the list pads tool. Finally, we have some other ones. We have the documentation, very important, but we probably won't talk about it too much today. But there's a whole documentation system. It generates our API documentation and all that. And finally, there's the autoconf directory, which we may talk about depending on how things flow today. But that is a way to automatically build the model without MKMF. So what is in the model? So we'll start with config source because it is sort of where everything starts. So in config source, there's another directory called drivers. That is really the program. That's where you start. That's the main in C language. This is where everything is set up with the other models like the ice, the ocean, the atmosphere, etc. And you're not really getting into MOM yet. This is really the glue code. There's examples here of ocean only, which we've been using. There's also ice solo, which runs with sys. And then we have the last three, which are genuine coupled models. We have FMS cap, which is what GFDL uses. We have nuopc cap, which is used by a couple other groups that I listed here. And MCT cap, I don't know if anyone's using that anymore, are they? Okay. Okay. Yeah, MCT is a coupler framework similar to Oasis. And I guess it's there for a bit legacy support, but same idea. These are the guys that run the model. So if you were to get hired by some government agency and create your new coupled model, you would start by making your own cap in the same way. So this is not literal code. If you try to compile this, it won't run. It doesn't have the right number of arguments, etc. But the general idea is that you would initialize your model. So you'd run initialize mom, which is a real function, and then you'd go through some stuff and then you'd finish it. And then generally you'd go on to initialize all the other components of your model. But then there would probably be some sort of top level loop that you would run through. And that would probably have some kind of more sophisticated calendar that would keep track of all the Gregorian nonsense and all that. And so you would be updating the coupler wide fields, like the fluxes between the components. And I put update time because you'd probably have to do some calendar update as well. But then inside that loop will be a smaller loop of steps of the components. In this case, we're just stepping through MOM. So really step MOM is sort of the first function where you enter into MOM itself and start running MOM code and running MOM solvers. And so the point is that when this is set up, I mean, although it's not literally true, in a lot of ways, MOM is kind of running on its own and is really only aware of the other components through its fluxes and a few other select functions. And so it's kind of doing its own thing in its own world. And so a lot of ways you can talk about the behavior of MOM without talking about the broader system around it, which is by design. That's a good design. That's encapsulation. So just stepping through some of the other configurations you want to go through. I did mention we would talk about memory later. We're still going to talk about it later. But that talks about how we implement our grids. There are two principal ways we do it. Infra, again, this is where you would insert your own way of doing sort of lower level operations on the machine. So we have FMS 1 and 2. This actually reflects two implementations of the IO inside FMS, which, as I mentioned yesterday, is GFDL's sort of framework library. Hypothetically, you could do additional frameworks. We could invent a very minimal one that only works on laptops, for example. We could use ESMF, which is another UCAR. I got that. So there are other frameworks that could hypothetically go here because, again, as I said, MOM sort of can do its own thing without worrying too much about the coupling details around it. And then finally, we have this external directory, which is becoming more interesting by the day. This is really a place to deposit and configure things. Like we have so BGC is the biogeochemical cycle. We have a very inert, almost missing BGC in our repository, but hypothetically you could put a much more interesting one there, like Cobalt or whatever. And that's the same idea with all these components. So there's ODA, data assimilation. We're currently working on putting Python interfaces so that an instance of MOM can actually talk to a Python instance running, so they can actually communicate. And we recently just merged some code to let MOM interface with an external database. It's either Redis or something like Redis, but the point is that this is really a space where MOM doesn't have to just be running a bunch of Fortran code and solving equations. It can really start to engage with bigger software projects. And it's no surprise machine learning is motivating a lot of that. So that's sort of the glue around MOM. But if you want to get into the components of MOM, these are some of the directories. I can't fit them all on the slide, but core is sort of the main solvers. This is where the main loops happen. Step MOM happens in there, initialize MOM, and it does have genuine physics and solvers in there, but it's sort of the necessary components. It has other software-y things too, like IO and stuff. But a lot of the scheme, particularly if you're doing research and you want to introduce a new feature or other, they're much more likely to go to these other directories. Parameterizations is the most likely. Tracer physics is happening in here. It's sort of, it could exist in a few places, but that's where it happens to be. A lot of the vertical remapping that Steve and Bob talk about, the solvers for doing that are in the AL directory. And then we have diagnostics, which is really more maintenance. It could have been removed from this slide, and I don't think anyone would have noticed. It's really about management of the diagnostics. Or there are actual genuine diagnostics computed in there as well. I'll take that back. These things don't always reside in the most logical place, or they're historical. And then user is an interesting one as well, because although we have ways to let you put in arbitrary topographies and force things as files, I think as a lot of you have come to see, there are a lot of pre-packaged things like C mounts and topographies and things like that, and wind forcings that you can just turn on and off for convenience. And the user is a directory where that stuff, it's kind of meant to be user code where users would put in their own versions of that stuff. That is probably a place where people might be interested as well. And there are other things in here, but I'm going to skip over them. So looking in the model, how does it look? This is the simplest module I could find. This is the geothermal module. So we do write in Fortran. We're still living in the 90s, although I think we do a pretty good job modernizing it. So we have a one module per file rule. So we try to follow Python in that respect. I mean, not intentionally, but it resembles it. So we tend to structure it so that, excuse me, my mouse. We're very explicit about our dependencies. So that's a somewhat unique aspect of how we do things, but we say explicitly what we're going to use in this module and everything and where it comes from, which is kind of a pain from a coding point of view, but incredibly useful when you're trying to figure out how these things work, because these are somewhat older languages and it doesn't always map out where everything is coming from. And so we need to kind of do that work for them. And going in, we also have a public interface. So we do explicitly say what functions you can and can't use from this module. Generally speaking, we assume that if the function is in there, you probably can't call it unless it's explicitly put in this public statement. And the other feature is that we have these control structures. And this is kind of our way of doing something like object-oriented programming. We hide the details. These are all the variables and stuff that are needed to configure the module and all the operations in it. And we explicitly make them private. So with, unless it makes sense to expose it, but for the most part, we hide information between modules. If you have a field and you want it to be manipulated, generally the way you do it is you would call the function, provide the field you want to change, like say thickness, and then you would supply the control structure, which is how you would manage the operation, say with the parameters in the MOM input file. And that's how things happen. So that's kind of, I think if you take all of that and got it together, we're doing about 95% of what object-oriented programming is intended to do. We just don't have all the syntactic sugar that more modern languages, well, actually Fortran has it as well, but we don't use it. We're getting there. I'm not intending to go over this, but just for a glimpse of how things look, you can scroll through this file and we're going to come back to the various styles and mannerisms in there. I have said all this. The one thing I missed 2 points. One is we don't have variables in our modules. That's if some of you, now you guys probably are not sucked into Fortran like us old folks, but it is possible to put variables in modules, but what happens is they end up being global and persistent, and basically there's hidden state. So we don't want state. We want functions to do exactly what they do all the time. We want them to be predictable. And if you're depending on variables in the modules that can change, that screws with that entire model. So it's not fair to say we're doing functional programming, if you're familiar with that, but we are trying to embrace that component of functional programming. So the other point is that we do document these things. These are Doxygen syntax, these little comments with the arrows after them. The arrow says which way it's commenting at. So this arrow is pointing rightward. So we do require pretty strict rules on documentation. For those of you that have submitted code and gotten documentation errors, this is why. You have to document every variable in your module, in these types, these derived types that we have, and every function and every input to the function. So I don't know if we'll have time to come back to this, but that is an important component. So we have all these things and they do help modernize the language for us. What is the model doing? I'm just going to check the time. So we have these three. So I would say StepMOM is really broken up into 3 major steps and dozens of minor steps, which I'm not going to talk about. But you could break it down roughly into the dynamic step, the thermodynamic step, and the tracer dynamics. Although I think thermodynamic might be better called diabatic forcing, because things like the equation of state actually happen in other places as well. So the dynamic, again, could be thought of as kind of an outer step and an inner step. The outer one would be things that sort of modulate the general fluid solvers. So the GM diffusion happens in the dynamic step, bottom drag, sub-mesoscale, Miki. But then, so those things sort of modulate the inner step, which is much more of a traditional fluid dynamics solver. So this is doing kind of calculation of accelerations, it's updating the velocity field, and then it's doing the inversion step to get the pressure. Although in ocean models, we avoid a lot of the traditional complications of doing that through the hydrostatic assumption and other things. But but if you break down the main steps in the dynamic, the Runge-Kudich solver, there is the Coriolis calculation, there's the pressure force, there's the vertical viscosity, there's the barotropic step, which Bob talked about a lot yesterday, where we do the split time stepping inside. And then there's the continuity solver, which is generally the scary part of a general fluid dynamics model. Not so bad in ours, but it is very heavily in the finite volume solvers. And then finally, we have the horizontal viscosity. There are many other things going on in here. These are just kind of highlighting the sort of steps happening in there. And then if we go to the other terms, the step thermo, a lot of that is happening in the diabatic driver. That's where things like KPP happen, CV mix, which is kind of same family, the geothermal term, shortwave. So the things that kind of insert or remove heat into the model. And then there's two modes that run in, of course, the diabatic and adiabatic. If you turn on adiabatic, this function, the diabatic function, well, the function that calls them probably arguably doesn't do a whole lot. It's never true that they do nothing. There's tons of little corrections. And if you look at the code, it is pretty daunting. But I think this captures kind of the critical steps in those functions. And then finally, tracer is, again, lots of little things. But and I guess Bob's going to talk about the actual tracer solvers next. But you could kind of break it down into the advection and the diffusion. So the advection is actually broken up into two functions because I think because the finite volume is so messy, it's just difficult to kind of consolidate those operations. But the diffusion includes the neutral diffusion. And there's also tracer vertical diffusion in there, but it actually gets called in the diabatic term. But that's sort of roughly how that's steps through the files and functions that you'll generally touch when you're running the model. I mentioned this PKG term directory before. These are our external code that we pull in. CV mix has come up a couple times. The equation of state is, I guess, optionally turned on to be TEOS 10, which is the complicated one based on enthalpy. It's Gibbs, thank you. So it's called GSW, global Gibbs seawater. Okay, yeah. Anyway, we don't actually maintain that code. We pull it in. And I mean, I'm working on ways to avoid that, but well, that's not a conversation for here. Okay, so that's the code. That's sort of, if you were to quickly step through the code, those are kind of the key points that I would at least call out. For next part, I'm going to talk about sort of how we represent this stuff. So it probably doesn't surprise you. We put everything on grids. One of the great strengths of Fortran is it has intrinsic support for multi-dimensional arrays. And believe me, we're not switching languages until the other language has that at the very least. So we have what you might call the Northeast Convention. I don't know to what degree Raf mentioned this, but if I talk about Arakawa grids, does anybody not know what I mean? Would anyone like me to discuss that? Oh, okay, then you should have gone first. I almost was gonna ask if we could swap, but okay, so we'll get into that. But just very quickly, there's a notion of a cell, and there are fields that are best represented by the center of the cell and fields represented by the faces and the vertices. I'll try to avoid not stepping over Bob too much, but things like thicknesses do sort of describe this cell in the center, and velocities are more naturally described on the faces, and things like vorticity are more naturally described on the corners. And really, it's the derivatives the natural derivative stencils that decide where these things align. And we follow the the Northeast Convention, where so we have the number by integers. We have to count these things. Sometimes you'll see in papers half integer steps in order to explain where these things reside. We can't do that on a computer. They don't know what a half of a memory step is. And if they did, I don't think we'd want to do it. So we follow the convention that IJ refers to the center of the cell or the eastern face or the northern face or the northeast corner. And you just have to know what it is based on what the field is. When we talk about these domains, we have to, well, first of all, I'll get into the parallelization later, but we have to pump these up. We can't just talk about the physical field, because if you look at this example on the bottom, any numerical stencil that has any kind of derivative is going to require values beyond the stencil, at least beyond the compute domain. Now that could be boundary conditions, that could be periodic, that could be from an adjacent domain in a parallel system. But so we talk about the compute domain, which are the values that are sort of physically represented in the equations. And then we talk about the data domain, which sort of represent an overflow where we can sort of continue to apply those calculations. So MOM has this, these are really FMS concepts, but there's this notion of compute domain and data domain. And you can see there are indices, which I'll come back to in bigger print, but the ISCs refer to the compute, ISDs to data, and then these Bs that we put on the end. I don't know what the B stands for. Does anyone want boundary? Okay, there you go. They refer to the vertices of the cells. So we have a structure called an ocean grid type. It's called G. You might have seen it in that example module. So that is where we store these indices so we don't have to track them. So for example, this is a very naive loop here of where we might update, say, a layer thickness. We would loop using the G's from J to J outer, I inner, and then we would do the computation. And of course, since it's a thickness, we use the C's and not the B's and not the D's. Well, we rarely use the D's, but we don't use the B's is the main point. So now finally, in great excitement, I know you're all excited to learn what was the hell that symmetric memory thing was. So now we're going to finally get to it. So there are two methods to represent these fields. There's what you call symmetric and non-symmetric. The symmetric says that we have an extra row of points on the western and southern rows here. Now, the reason you wouldn't want to do that is in most cases, they are somewhat redundant. For example, in a periodic domain, the eastern and western values will be identical. So you're sort of putting yourself in a position to have duplicates of the values, and you're adding work to keep those in sync. Similarly, if you had a rigid boundary of some sort, you already know what's going on there and you can apply that. But when you have a symmetric domain, you also can kind of do the entire calculation in a single stage. So it's much more efficient in general. It's much simpler to understand because you can just populate those values with there depending on the circumstances. And I think on top of everything, in order to do something like open boundary conditions, you must have symmetric domains here. It's just practically not possible. It's not impossible, but it's not practical to define boundary conditions along those faces if you're trying to define boundary conditions that are coming from something else. The one trick here is that the values of the indices don't actually change. So you don't actually need to necessarily know this when you're running it. You only need to choose it. So the I's and J's values don't change. But Fortran, another great feature of Fortran is it allows arbitrary indexing. And what we would do is say if this ISD B was a 1 here, we would initialize it as a 0 over here. The ISD, however, would be unchanged in both cases. Those are always indexed by the same value, 1 in this case. So for the most part, I think the design is set up so you don't have to think about that very much. Because as I said, the main point is the I's and J's don't change as you move from symmetric to non-symmetric. It's just you're adding an extra row of zeros on the symmetric case. Now, the part where this gets weird in MOM6 is we do provide macros to implement this. So when you declare these arrays, you're going to have to keep track of whether you initialize it as a 1 or a 0. And so for starters, we have these macros stored in this header file, MOM memory, where we apply these. They are essentially functions of this G. They don't actually end up appearing as calculations as function calls like this. They end up getting kind of substituted by the preprocessor. But these will set up whether or not these guys are 1 initialized or 0 initialized. And then we also support something called static memory, where all the arrays are predefined at compile time. It's hypothetically faster, but I'm one of the skeptics. I think you can actually get good performance regardless of that. But there was a time when static was a big deal. I'm not going to talk about static too much, but it's if you know what I mean, it's a feature. But that's another feature provided by these macros. But I would say if you are allocating and creating a function and you need to be aware of those starting indices, I would say at least look into these macros. You definitely need them when you're creating new variables. Passing them around, you can probably avoid it to some degree. So I alluded to parallelization. How do we parallelize? Well, we traditionally take our domain and split it up into a whole bunch of little boxes. And then we run each box as if it's a little microscopic ocean model. And then we do these halo updates in order to refresh those data domains across them. So in this case, imagine one of my little domains is rank 25. It's just an arbitrary label for a subdomain of the ocean. I would run the model over the compute domain and extend those to any halos necessary. And then I would do this message passing step where I would refresh the values. And that's a lot of communication. And depending on the circumstances, this can be an enormous bottleneck on the model. I think the actual nature of the performance of this changes a lot as technology changes, and things that used to seem very slow are actually not very slow anymore, and vice versa. So, but it is something you have to monitor. And I do want to comment that for every single domain that we run, so if you parallelize this on 1,000 ranks, every time you need to update your fields, you need to send 8 messages to its neighbors. And that's because we do separate messages for the sides and the corners. And I will mention that there are other ways to do this. For example, the UK's weather model, the does a 2-pass system, and other models do as well, where they do all the north-south in one wave and then all the east-west in another wave. And that actually, if you want to do it in your head, you can see that works out the corner issue. And so it has technically fewer messages, but the downside, of course, is that you have to do it in 2 stages. You have to do this big communication operation, and then you can do it. Then you have to do it again. Whereas this, you can stage it all at once, and then hope that it's faster to do it all at once. And this is what I mean when it's hard to know which is faster. It's not really obvious. Most of the time, though, this is not the bottleneck that people often think it is, in my experience. So it's good to know. So how does this work in the code? Well, we have these functions called group passes. If anyone is anyone here, I'd like to know, are people familiar with MPI programming, and has any of you even done it before? Bob has? I see 4 hands. Okay, we'll say 10. Okay, yeah, this is kind of an interface to FMS's communication layer, which is an interface to the MPI layer. So, so what this does is it lets you set them up in advance and then trigger them, or it lets you stage them to run in the background while you're doing something else. So I have a very simple example of that here. Like this is updating the halos in, say, the velocities U and V. You could set it up here. This might be in your initialization function, and you tuck it away in your control structure. And then later in your actual solver, you might do some calculations on U and V, but you now need to refresh that to the other MPI, the other ranks, the other domains. So you could either run it, you could either do what's called non-blocking and just start it up and then go do something else, because it is an external operation. And then if you're non-blocking, you would say, all right, I did my other stuff. Now I need to know that's finished. And you would wait here at complete group pass. Or you could just say, well, I'm not going to deal with all that kind of that concurrent programming is too hard. So I'm just going to do group pass and say, just do it now, and I'll just wait till you're done. So I sort of stuffed both examples in there. I hope that didn't confuse things, but I wanted to reduce slides. But the idea is that you can do it either way, and that's how these functions work. And I think overall they're quite a good interface to that, which is, if anyone's done MPI programming, it's very messy. So another thing you will see scouring through the code are diagnostics. So register diag field is how we do this. I'm not going to go over all the arguments, but you can kind of figure out what they are. One is that module that you would have seen in Alistair's talk for the diag table. You have a name for the diagnostic. You have the location of it. This is axes T, so that means it's on an H point. There's the time. There's a description of the diagnostic, the units. And then this is something we do for dimensional consistency. We actually specify the physical units of it. And this comes back into our dimensional testing, which I think, unfortunately, I had to remove from my talk, but we can talk about it if there's time. So you would do this in your initialization, and then later in your model, after you've done some work on this variable KHH and you've computed it, you would call post data, and that would be the action that sends it to the netcdf files that you guys saw yesterday. And there's a link to the API if you want to see that. Another component of MOM is getParam. These are how we define those parameters in MOM input. So again, this one's a little heavier, so I won't go into it. You can probably figure it out from the arguments. But what you can see is that this will let you add new parameters to the file. So as Bob mentioned yesterday in a comment, parameters are better than fixed constants. We don't really have fixed constants in the model anymore. You know, even stuff that might be pretty standard, like gravitational acceleration and radius of the Earth, those are all configurable as they should be. And so I think that's the correct direction to go. And this is how you would do it. And finally, checksums is another feature that we have. This I will talk about this more in the after the break, but this is how we validate the model. Putting these in can be very useful. Generally, you want to wrap them in a debug flag so that they don't run in production. They're not cheap. But they will provide you very robust measurements of a kind of bit reproducible detection of the fields. Timers, you'll also see a lot. These are how we measure the computational performance of the model. They're quite easy to set up. I think a lot of the difficulty is wrapped up. And a lot of this comes from FMS. So in the site initialization, you would call this function, you would assign an ID to it, as you would have with the diagnostics too, by the way, which I skipped over. So yeah, it's ID based. And then any task you want to clock, you put begin and end around it. And so that's all I have. I only have 10 minutes. So this exercise, I kind of half intended to. I was expecting that this would be shifted over to the next session, but I think that's a pretty, I didn't get the summary slide in anyway. Yeah, so this is all I was gonna show. We don't have to do the exercise now, but I think we're gonna wrap up a little early so that people can maybe have a try at this. But yeah, we will come back to this, or we can do it now, but either way, that's sort of my summary of the code. It's a very rapid tour of a 200,000 line project. And if there are any questions, I'm happy to do that. Or if people would like to give this a go, we can do that. Oh, then we're not doing this. So let's do questions. Yeah. Yeah. Sure. Mm-hmm. Oh, we preset those. Where's the slide? So we have a fixed halo of 4 actually, and it's pretty global. What we do also have though is an ability to reduce the amount of data you need to send. So that's I don't know if that 4 is configurable. Is that hard coded in the model? It is configurable. Okay. 4 is pretty generous. It's very rare you'd actually need that much data. This wasn't your question, but often the bigger question is how far do I need to do my calculation? Because if you look in these functions, I hope you don't mind, I'm hijacking your question. What you often find is that, this step will depend on a derivative and this one after it and this one after it. And you'll find that you're kind of creeping out into the halo as you go further out. And this can be even more complicated as you're jumping between those center points and edge points. And so often the difficulty when working with these is to know how far to extend your loops, because your loops generally may need to go beyond the compute domain in order for the next step's compute domain to make sense. So that is related to your question, but that's one of it's a difficult thing. And I feel like it's something with a lot of work, we could sort of bake into the code and have it know, but currently it's just the burden of the designer. Yep. Oh, I don't know how to turn it on. But.
Relatedly, though, on this specific point, if you change the parallelization and you get the right answers, then your halos are wide enough. They may be too wide. If you change the parallelization and you get different answers, then your halos are not wide enough, or you need more halo updates. So there's a very pragmatic answer. And that's one of the tests, and I think we're talking about this later, that we routinely run through. We make sure that the answers are the same, regardless of how you break it up onto processors.
Yeah, that's exactly right. Empirical is the right answer. Do we have time? Go ahead. Mm-hmm. Oh yeah, that's right. Yeah, that was mentioned in the second session. But yeah, this is as good a time as any to mention it. We have a soft convention, and thank you for bringing it up. We do lowercase I and j on center points and capital I and j on edge points or vertex points, and we can get away with that because Fortran doesn't care. So Fortran's a great language, whatever you might have heard.
Yeah, the second question was, you talked about the diagnostic related functions, the get param or so, and there's also an argument scale, right? I think that didn't appear here. Oh, okay.
This is for parameters and diagnostics. I suspect your question's the same, but.
Right, so there's something like conversion and there's something like scale, right? Yeah. So what's the difference, and when do you use what?
I'll talk about, I think it's conceptually is easier to explain here. Actually, it's the same point. So again, I think this will be alluded to later, but we have something in the model. We have a dimensional scaling feature where we can establish the dimensional consistency of our equations. I have kind of concluded we probably don't have time to explain how it works, but I'll just quickly say multiplication by 2 is bit reproducible. So it allows us to scale up and down these variables in proportion to their proposed dimensionality. So in this case, it's a viscosity. It's going to be meters squared per second. We can predefine scale factors for those units, and we can construct a general rescaling factor for this quantity. So if it were to appear in an equation improperly, and we were to apply those rescalings, you would get a different answer. And so that's the purpose of these. They also sort of fulfill a self-documenting component, which is really nice. But internally, that's their purpose. So I think that's because yeah, because so scale is kind of bringing the parameter into the model, and conversion is taking it back to its original form when we write it to the output. Did I?
Yep. And so if you look at any line with a conversion, you can compare that with the units that you declared if they're on the same line. And there's only one right answer. If it's meters squared per second and you're converting, you have to be converting back from meters squared per second. Whereas if you go to the next slide, Marshall, this is also meters squared per second, but the scale is going the other way. And so you can grep through the code to figure out if the units are right. We know that the scale and the conversions are right because when you run the model and you change the internal representation, you get the same answers. Otherwise, so we know that every scale and conversion factor is right. And by using the scale and the units, it's a way that we can grep through the code and spot any cases where the documented units of the input variables or the output diagnostics are wrong. The other thing, there's a few places where we use scale where we really should be using conversion, and that was because we only figured out after the fact that we could do this. Those are the cases where there are not units to compare to. The good news is there's only one scale or conversion argument to any of these calls. So you can't accidentally put the wrong one in and have it compile. If it weren't for the fact that it would lead to hundreds of lines of code changing, we would take the checksums and turn them from scale factors to conversion factors. But that would be a whole lot of lines of code changing, and that would make people unhappy.
Thank you, Bob. Okay, I think we're out of time and Bob's up. So if there's any other questions, we'll, bring them up throughout the day. I would suggest at least having a look at this. And so while Bob's getting set up, this is just an idea, a proposal to try to add your own diagnostic in the code. I put a recommendation of entropy density because it's so easy to do. Just look for the vorticity and square it. Yeah, if you want to do this, I don't mean to propose to do it during Bob's talk, but if you want, we'll kind of see how time goes in the next session. And I have a backup example that doesn't require this, but if you want to kind of at least browse the code and see how to do it, it's one of the most likely, if you are to do anything with the model, this is probably the most likely thing you are to ever do with it, which is add an additional field you care about. So stop there. Thank you.